Okay, let's start. So based on the survey sent out last time, we'll have the final exam on May 31st, Monday evening, 5:30 to 7:30. So I also posted a few sample exam questions. So there will be many multiple choice questions. So the attack named multi-mobile buy targets which type of sensor. Can SOD system be composed of multiple SOD subsystems? And so on PID control, Twiddle, AlphaGo, and questions on IR. So this is a more concrete question, larger question on reinforcement learning with the MDP shown here, and you need to perform the steps of different IR algorithms by hand. So, so hopefully this gives you some idea of what to expect in the exam. Also, I added a link here in the lab 1, added a link on a person's open source model for the German traffic sign recognition problem. So he used ResNet and did the transfer learning. So first, you open up the data set, and use the transfer learning to so you start from the pre-trained ResNet and create the instance. Yeah, I think he retrained the whole model with no layers frozen. But that's your choice. You may choose to freeze some layers, or
I think he used the model, but just added a new classification layer at the end because it trains in just 2-3 minutes.
Carly, it seems we cannot hear you clearly. It's very low volume from your side.
Okay, sorry. Yeah, I will see.
so he added a new softmax layer, right? Yeah, you have to do that. So and also I think it did not freeze any layers. He just retrained the whole network, which is obviously okay. But if you don't have enough data, or you don't want to spend too much time, you may want to freeze some layers. It's all up to you. So
do you hear me better now?
yes.
Yes.
Yes. So I think I just had a quick look today. It's very useful example anyhow. It's very good to read through the code. There's a lot of nice things he shows in the examples. And also in the blog, there is like a book in deep learning, so it seems very good as well. But as I understood, he took the ResNet and then added just a classification layer because the ResNet has much more classes, and then just trained it for 4 traffic signs in this. But I haven't studied in detail, so I'm not completely sure. But yeah, so
Oh, these 4 signs. Okay.
Yeah. And then he retrained it, the classifier with a 5th sign unknown to see if it could detect. And then he took a random choice from the other signs. So if there was some strange sign, it could classify that as an unknown sign in the very last example. So, but I don't think you can retrain ResNet in 3 minutes. So, but I am not sure, but it sounds a little bit too good to be true.
Yeah, if you only have 4 classes, then it's a much easier job. Give away, no entry, priority, road, stop. I think he only trained for the 4 classes. So that's a very easy task.
Yeah, so.
I'm also trying a similar approach, trying out both ResNet and LNet. But what I discovered is for the ResNet, you need to resize the image to 224 by 224. And I think it needs 3 channels.
Okay.
Yeah, I think the ResNet architectures, I think their input image is 224 by 224, as I've discovered now.
Yeah, if resize 64.
So I think he resized to 64 by 64. And this is data augmentation. So you don't have to do this. You don't need to, this is an optional step. But ResNet, ResNet has a multiple variants. So I think he used a smaller version of ResNet. ResNet 34.
Yeah, and it says pre-trained true equals true. So I guess in the line you showed right now. So I'm not sure if this pre-trained means it's frozen.
No, the pre-trained means you start from the pre-trained parameters. So ResNet 34 is a smaller version. So you see,
Okay,
yeah.
so maybe it's quick enough. Yeah, it could be, absolutely.
The image input size is, I would expect the input size is 64 by 64, but I could be wrong.
It looks like a 7x7 convolution on 64, the first layer.
Oh, yeah, okay. Yeah, so depending on your choice of ResNet, if you chose a larger ResNet model, maybe input is larger in pixel size.
Yeah, I'm trying ResNet 50, and I think the input size seems to be 224 by 224.
Yeah, but that is a more bigger net than the ResNet 50. It's very popular. I think they think the ResNet 50 is the best ResNet or the best network because it's not so big but still very good and fast.
Yeah, if you don't like the input size, you can always manually change it. For a ConvNet, it's not difficult. If you change the input neurons, number of input neurons, it'll work.
But I don't know how you change the number of input neurons in a ResNet pre-trained, so to say.
Actually, I have tried to make it as a MNSIT dataset similar to 2828 with this traffic sign.
Yeah, that works fine because most of the images are really small.
Yeah.
Yeah.
And that color also I have converted to gray and white, that black and white. I'm doing it on my local system, so processing is one concern.
Yeah, so this video and the blog is useful for if you're not familiar with PyTorch or Colab. It teaches you the basics, the mechanics of opening the data set, getting it into PyTorch, and how to get the labels and so on. So especially the early part of the video could be pretty helpful. Yeah.
And also the book or the chapters in the book seems very nice as well. As you, yeah, either in the book paper version, but you can have it online for free. You have the links beneath in the blog, not there, but in
Okay, but is it free or not?
the book costs on paper, but it's free. The website is free. So there is a list of examples. I think on his blog, you have the blog link for him. Let's see where it is. At the end, here. Getting things done with PyTorch. There's a GitHub.
Okay.
Read for free. I can send it in the chat. I find it. So now I have it in the chat, so you can have all the chapters and read for free.
Oh, the whole book can be read using the links
Yeah.
below. So it is indeed a free book. So that's good. Yeah.
Yeah, very, very good catch from you, Sungwa.
Yeah, the book link is at the bottom of the YouTube video. So it's GitHub, getting things done, or getting things done. Yeah, I think this is the link. Yeah, you can find it in the link. Okay, thank you, Vanillian Volkov, the blogger, for your hard work.
From Bulgaria.
Okay. So I hope you can finish the project. So if you really have difficulty, take his pre-trained model and do some attacks. That works. That's fine. But you maybe lose some points. So we continue with our lecture on adversarial robustness. So let's just briefly review what we discussed before. So the robust ML, the main problem is to find a perturbation delta within a given bound, a bounded perturbation to the input, and try to maximize the loss. That is to try to fool your classifier into misclassifying into a wrong label. And then that's the attacker's job. And then as a defender, you may add a minimization loop, outer loop, to try to train your model against these attacks. So that's the next half of the lecture. So the first half is on attacks. So we discussed all the norm definitions. So we mainly focus on the infinity norm with the square shape and the L2 norm with the round shape. And this example shows that L infinity norm cares about the maximum change to any single pixel, whereas L2 norm cares about the overall change across all the pixels. So, the idea is that this is the loss function surface, and you're given this bound large delta, and your goal is to find the maximum of this point given the range. But this solution is intractable in general because the neural network loss surface is non-convex, non-linear, highly irregular. So you cannot, it's an NP-hard problem to find the exact solution. Therefore, you need first a gradient ascent local search to find the local maximum, and then a formal methods for finding exact or relaxed solutions. So the first is the local search method. So we can draw an analogy with the gradient descent for training a neural network, where you minimize the expected loss on the training set by adjusting the neural network parameters. Theta includes neural network weights and biases. Whereas for adversarial attacks, you are trying to maximize a loss for a given input X by finding a perturbation delta. So, so the key difference is that first, the horizontal axis for training a neural network is the neural network parameters, whereas the horizontal axis, the adjustable parameter for finding adversarial input is the perturbation. And also, this training a neural network, you are minimizing the expected loss over the whole training data set. Whereas for the adversarial input generation, you are maximizing the loss for specific input, for specific image. So you need to run the attack on every individual picture, every individual image. So attack is image specific. So the basic idea is that you are taking a gradient ascent step based by taking a derivative against the delta of the loss function, and add a weight, the learning rate term, and add it to the delta value. Except because you have the constraint on delta to be within the range of L infinity or L2 ball within the constraint range, you need to project the delta back into the L infinity or L2 ball if it goes outside of it. So that's the only difference. That's the only complication you need to consider when you are doing the optimization. Whereas you don't have this constraint for neural network training. You can go anywhere you like in the parameter space. But here, we are constrained to lie within a given range. The idea is to minimize the perceptual difference from the input so that it's imperceptible to human eyes. So the FGSM has this idea that it's always a good idea to look at the corners. In a two-dimensional space, they have 4 corners. In the higher dimensional space, you have more corners. So whenever you take a gradient step, you always take a very large step by taking a very large learning rate alpha, so that it goes outside of the area infinity ball, and then you project back by the clip operation. So this operation results in a corner, assuming that your initial step is very large. So if you're in the this quadrant, anywhere the gradient direction is in this quadrant, you take a large step and project back into the corner. Anywhere in the other quadrants, say in this part, you project out and then project back. So here are the example images. So in your project, yes? In your project assignment, you would see similar patterns. So essentially, the attack adds some background noise to the image. So the idea of preferring the corners is very intuitive. So suppose you have 2 classes, the cross and the circle. And this is the classification boundary. So if you want to attack this image, and you want it to be the perturbation to be within the L infinity ball, this square, and you want it to cross over the boundary to the other class, then it makes sense to attack, to move it to the corner. Especially for linear models, this attack FGSM of preferring the corner is actually optimal. So in this case, the attack is unsuccessful, but with a larger perturbation, perhaps with a perturbation like this, then this corner crosses over. So if you move the image, perturb it to here, then it'll be misclassified. So there's a proof. The math is not important. The intuition is important. That for a linear classification boundary, indeed, picking the corner is an optimal strategy, but not for a nonlinear classification model like a neural network with the ReLU or other nonlinear activation functions. So imagine the classification boundary is not a linear line, but something like this, very irregular classification boundary. Then suppose you want to attack this image, this input, then the optimal direction is here. So, and not in the corner. So if you move it to the corner, this particular corner is not misclassified. But if you move to another direction in here, this point will be misclassified. So, so for a nonlinear model classification boundary, moving to the corner is not an optimal strategy, although it's a good heuristic. So, so this projected gradient descent is a better strategy than FGSM. Instead of taking a single large step to the corner, you take many small steps. And I added a line here. It shows the final data to end up at the corner of the L infinity ball, but it may not be in general. So the figure shows that it falls into a corner, but in fact, it may very well fall into some other point on the boundary. So this is because for as I just mentioned, for a nonlinear classification model, the corner is not always optimal. So PGD, by doing this gradual small step gradient ascent, it's able to find a better solution in general than taking a single large step to the corner. So the steepest descent is really a performance optimization over the projected gradient descent. So the main issue is that it's difficult to choose the learning rate alpha. So the rule of thumb is to choose alpha to be a small fraction of epsilon, the epsilon ball, and set the number of iterations to be a small multiple of epsilon over alpha. But sometimes the gradient in the tutorial, they showed an example where the gradient is really small. So you need many thousands of steps before this PGD converges. To improve performance, this projected greedy steep descent essentially lets you adjust your learning rate automatically. So if your gradient direction is in this arrow direction, you adjust it to point to the corner with the alpha L infinity alpha ball. So in this way, if you have picked an alpha, and by using this formulation, you're accelerating your convergence. So going back to the picture here, so essentially you're taking a many small alpha L infinity balls. So this is alpha ball. So this is the alpha ball around the origin, the original image. Suppose your gradient direction is perhaps pointing to here, but instead of going in that direction, you go towards the corner of the alpha ball in this direction. And that's one step of gradient ascent. And then in the next step, again, you take a alpha ball around the new point and follow the gradient to the corner instead of the original gradient. At every step, you take an alpha ball and go towards the corner. So you can imagine many of the small alpha balls at every step. So this gives you faster convergence because intuitively going towards the corner is a larger step than going towards the general direction. So it's a performance optimization on top of a projected gradient descent. It's not a necessary a step. You can do without it, but with this particular optimization, your attack optimization can converge faster. So this this figure has some similarity with the FGSM figure in that they both try to choose the corner to go to, but the for FGSM, this is the epsilon ball. So you're going directly to a corner in one step. So that's FGSM. Whereas for PGD, you're taking many, many small steps with a much smaller learning rate alpha. Except at every single small step, you point towards the corner of the small L infinity box, L infinity ball with the size alpha. Okay, any questions? So as you can see with the PGD, you can get a higher success rate for your attack than FGSM. And then we discussed targeted attack. That is, you're trying to turn the classification label into a specific target label. Why target? From the original label Y. So you're trying to maximize the loss for the original label and minimize the loss for the target label. So if you plug in the loss function, the log negative log likelihood for the softmax loss, and then you have this expression is to maximize the legit for the target class label and minimize the legit for the original true label Y. Or you can minimize the legit of all the other labels except the target label. So you can imagine if you don't care about the target label, just simply remove the first term, then you have the non-targeted attack we discussed before. So that's just a special case of the targeted attack. So here the attack turns the label 7 into 0 or into 2, depending on your optimization objective. And then the pixel-based attacks are not realistic. You cannot easily modify the pixels in the video stream of a self-driving car, for example. So people have implemented physically realizable attacks. So here's the method. So because in real life, the stop sign may be viewed from different angles in different lighting conditions. To make the attack robust against these variations, they take pictures of the stop sign at different lighting conditions and angles and simply average the loss. So k-variance of the training input image. This way, by minimizing, so this is the minimization. It's just a simple difference in minus sign. So the formulation is just the same as we discussed before. And it's an untargeted attack. So you're only trying to deviate from the true label Y. Universal, okay, sorry, this is a targeted attack. Yeah. And also you have this term here. So added a sentence here. The objective tries to minimize the perturbation delta T norm instead of putting a hard bound on delta T norm. So it's a different formulation with a similar purpose. So yeah, I think I messed up the notation. So the Y star is just the Y target. I should really make it unified. And then if you look at our previous pixel-based attack, the attack result is adding some noise to the image. So this is not very easy to turn it into a sticker. So if you want to put a sticker on the stop sign and fool the classifier, then the attack pixels should be concentrated around a small region. Otherwise, if you have all the pixels salt and pepper noise all over the image, you cannot easily turn it into a sticker, a label, a kind of a graffiti-like sticker. So that's why they added this mask M to localize the perturbation. So and then in the first term, they used the one norm to find the most vulnerable regions because L1 loss promotes sparsity. It pushes most terms to 0 and only leaving a few non-zero terms. So this forces the perturbation to be concentrated around a small region. So this is the result of the mask. This is not selected by the designer. This is trained from the L1 loss training process. And so this is the result. So this is a love, a hate, the two stickers. This is some black and white stickers. And I think these two are custom images they created. So this is another attack, physically realizable attack on face recognition. So they 3D printed these funny pattern eyeglasses. So the classifier will misclassify this person into a different person. So they notice some points. So need to find perturbations that generalize beyond a single image. That is, the eyeglasses should work on different people's faces, not specific to a specific human face. The technique is similar to the previous technique, just doing a simple average of multiple variants of the input image to make it robust against the input image. Just try it, average loss, use the average loss across many input faces. And also make the perturbation form large patches to make it easier to do the 3D printing. Because if your attack has very different pixels in a very small regions, the 3D printer may not be able to capture the very subtle variations. So it's good to have large patches of colors concentrated to make it easier to print. And also you should try to craft perturbations that the printer can actually produce the color. Yeah. So that's all white box attacks. That is, to perform the previous attack, you need to take a gradient step against the input. So the gradient step, for example, yeah, so if you want to take a gradient of the loss, you need the neural network parameters, because the loss is a function of the neural network parameters. So you need the input model, the neural network model, to perform the white box attack. But for black box attacks, you don't have access to the network model. So there are two cases. First is that if you have the training data set of the targeted black box model, for example, you know the black box model is trained on ImageNet. Then you just train a proxy white box model yourself and generate attacked objects for the proxy model. Or if you don't have the training data set, you can query, you can invoke the online cloud services to obtain many input-output data pairs from the target black box model. And then from the input-output data pairs, that forms your training data set for your own proxy model. And then you train the proxy model and perform the attack. So, so here's the, this is the targeted black box model you want to attack. And you don't have access to the internal parameters, so you cannot take a gradient, you cannot directly attack it. And you train a proxy white box model locally on your own computer. Either by having access to the training data set or by querying the target black box model over the internet. So, and then when you obtain the attacked input image from your proxy model, you simply feed it into the target black box model. It turns out that many attacks transfer pretty well. That is, you attack one model, the attack image actually works well on similar on other models. So the problem with the second approach is that it may get expensive if the cloud service is not free. Yeah. So this is the video we saw last time that they trained the adversarial examples from the YOLO object detector, which is a proxy white box model, but it also fools the faster RCNN, the black box model. So this is another interesting attack to generate some funny billboards like this or this. So the goal is to generate a single adversarial billboard image that may mislead the steering angle of an AV upon every single frame captured by onboard camera during the process of driving by a billboard. So top figure shows the kind of billboard you often see on the roadside. The bottom two figures show an adversarial billboard example. The Dave steering model diverges. So the correct steering direction is this, but it diverges to this direction or the other direction. So the workflow is, so the main challenge is to make the generated perturbation for contiguous frames, consecutive frames, because the car is driving and the billboard's viewing direction is changing continuously. So you cannot simply attack a single image, but you need to make it work for a sequence of images. So the first step of training dataset generation, they prefill the billboard with unicolor and paint its four corners with contrasting colors, the red dots, and record the videos while driving by the billboard with different speeds and angles. That's the training dataset. And then you generate a locally best perturbation for each single frame and find a single perturbation that misleads DNN's best for multiple consecutive frames using a joint loss optimization method. So, so this is a billboard. When you view it from one angle, it's this shape. When you drive closer by, maybe it turns into this shape. And the adversarial generation is based on joint gradient to try to make the perturbation applicable to be effective against multiple different viewing angles captured in the video. So finally, you transfer the RGB values to printable colors and physically print out this billboard. Okay, so this is another interesting attack of a phantom of the ADAS. ADAS is Advanced Driver Assistance System, so it specifically targets Tesla. So a phantom is a depthless projected picture of a 3D object. Could be a pedestrian, a traffic sign, a truck, a bicycle, car, traffic sign. So with the purpose of fooling the ADAS system to treat it as a real object and trigger an automatic reaction. So it could be done in different ways. So here is a McDonald's ad. If you notice, there's a flash, briefly a flash of a stop sign for a few 100 milliseconds. Or you may project a phantom via a drone equipped with a portable projector on the road. So this is a projected image on the road. And Tesla will misclassify it into an actual pedestrian. This is the phantom stop sign on the advertisement shown on the left. And Tesla will misclassify it into a stop sign. So let's look at the So the phantom was a picture of Elon Musk. So this is the McDonald's ad attack. Okay, so so the idea is very simple. So
Next up is Harsha Viswanath from Microsoft.
so the idea is so the whole point is to choose a specific area to display this stop sign or some other phantom image, and not to cause attention or suspicion by the human driver. So the bottom image shows the phantom duration versus the success. They tested two ADAS systems. One is Tesla, one is Mobileye. So for Tesla, you need to display it for longer durations to have effective attacks, minimum 400 milliseconds. Whereas for Mobileye, it's easier to fool. 200 milliseconds should be enough. So, so the thing is, they chose to display the, if you remember this, they displayed this attack image in this upper left corner. So how did they choose that? It's a very simple heuristic to try to find an area in the image that's least noticeable by the human. So the first step is to extract a key point as focus areas of human attention for every frame based on the SURF algorithm, which is a classic computer vision algorithm for extracting key points. So these are the green dots in this image. And then compute the local score for every block in the frame that represents how distant a block is from the focus areas, and embed phantoms into the dead areas that viewers will not focus on. So here, the red color, this color, the redder the color is, the more the human will focus on it. Whereas the peripheral areas, the green areas, are the dead areas that humans are not likely to focus on while viewing the ad. And then, so this is the dead areas for a single frame. This is the visualization of the dead areas for the entire video. And then you display the phantom, the stop sign or some other sign in at least T consecutive video frames based on this, curve. A longer duration leads to higher success rate, but also higher chance of being detected by the human. So it's a trade-off. so remember that we had this constraint of small data within a large data bound to try to minimize the perturbation and try to make it imperceptible to humans. This is a different approach. Instead of placing a bound data, they exploit the perceptual capability of the human vision system and pick the areas that's least noticeable by the human. So they also presented a Ghostbuster, a countermeasure. So when a frame is captured, the onboard object detector locates a road sign, and then it's cropped and passed to the context. This is a context model, a surface model, a light model, and a depth model, the 4 CNN models, and the combination, and finally a combiner model. So the context model essentially asks the question, would the signs go here? So it's a classification problem, yes or no. Is a sign likely to be here or not? And the surface model answers the question, is the surface realistic? And light model answers the question, is the light realistic? And depth model asks, is the shape and placement realistic? And given the 4 outputs from the 4 CNNs, the final combiner model, so each one produces so each one of the 4 models is a classification model, but instead of taking the output classification result, they take the next to last layer, the one just before the softmax. This layer contains the most high-level, most semantically meaningful features, and concatenate these layers, activation maps or feature maps, these 4 feature maps from the feature layers, and concatenate into a single vector as input to the combiner model, which you train the combiner model to make another classification of whether it's a phantom or real sign. So again, it's a supervised learning, so that you train the model based on real stop signs or phantom stop signs displayed by the attacker. With many training examples, this whole system of 5 models should be able to classify and detect if it's an attack image or a real image. So in the both the deep billboard and the phantom of the ADAS attacks, you notice that there's no data within large data norm constraint on the allowable perturbations. So this because they exploit different mechanisms for adding the perturbation. So the billboard simply assumes human drivers do not pay attention to roadside billboards. So the entire area of the billboard can be used for attack. It's actually true. I mean, most drivers don't pay attention. And the phantom of the ADAS embeds the phantoms into the dead areas that human viewers will not focus on. So the message is that the data norm constraint may not be fully aligned with human perception. So even though for the attacks, the billboard and the phantom of the ADAS, the attack image may have a data perturbation that's very large, but it's placed in certain areas that human perception system will not pay attention. So that's why actually the data norm constraint is a little bit controversial. People use it because it's mathematically tractable, right? You have a data, you can place bounds on it, then you can perform verification, perform gradient descent. Everything is mathematically nice. But in reality, a small data may not be the most effective attack. Sometimes the small data may be very conspicuous, whereas the large data, if you place it in the certain positions, it may actually fool a human. So this is not a perfect metric, perfect mechanism, but researchers use it because it's mathematically convenient. Okay, let's take a 10-minute break. Okay, so let's move on to the second approach of formal verification via combinatorial optimization. So that is exactly solve the objective. So consider a ReLU-based D-layer feed-forward network. So this is the input X. And every layer is a linear weighted sum of the input plus a bias, apply and then apply a ReLU, nonlinear activation function. So finally, you have the this is the legit. So the last softmax layer is not included in the formulation. So for the targeted attack in L-infinity norm, your goal is to try to so this is the neural network multiple layers. This is the last layer, last hidden layer, and this is the constraint, L-infinity norm constraint. So the objective is the EI denotes the unit basis, a vector with a 1 in the ith position and zeros everywhere else. So maybe an example is easier to understand. So suppose you have a binary classification problem. The correct label is cat, target label is dog. So the cat has the unit basis of 1, 0. The dog class has 0, 1 as the unit basis. Objective function is EY minus E target, which is, and take a transpose, which is a 1 minus 1 times the legit, which is legit of the true label minus legit of the target label. So minimizing this objective function tries to push up the legit for the target label and push down the legit for the true label. So this is exactly the attack, the formulation we saw before, except we had a minus sign. We have additional minus sign here. Therefore, we have a minimization problem instead of maximization. So for most MIRP integer programming solvers, the standard formulation accepted by the solver is a minimization problem. So that's why we do this a slightly different formulation. So this optimization problem is a mixed integer linear programming or satisfiability modulo theories problem. So you can feed it into IRP or SMT solver. So off-the-shelf solvers like IBM Cplex or Garobi open source solver can scale up to 100 hidden units, but the size depends heavily on the problem structure, including the size of epsilon, the epsilon ball. So one of the key aspects of finding the optimal efficient solution is to provide a tight bounds on the pre-ReLU activations. So lower and upper bounds are on these activation values. So here's the formulation encoding of the ReLU constraint with integer linear programming. So this max operator is not supported by IRP solvers like Cplex. So you need to convert it into a series of constraints. So the way to do it is to introduce a vector of binary variables vi with the same size. All these variables are also vectors. So with the same size as the zi plus 1, and then apply vector inequality constraint element-wise to the vector. So here's the formulation. Vi is the newly added binary vectors. So it appears in two places. So look at its two possible values. Suppose it's equal to 1, then this term turns into this term, and this term turns into this term. So, and these two red terms turns into this term. So greater than equal to and less than equal to. So the result is equal to. Or if Vi is equal to 0, then this term turns into this term. And this term turns into this term. The result is this term. So this is a clever trick of encoding the ReLU operator without the max operation, turning it into a series of inequalities.
I have a question.
Sure.
When Vi equals to 0, so where does the Li go in the final equation?
So let me see. So first, our goal is to encode the ReLU, which says that when the WZ plus B is greater than equal to 0, you should have output equal to WZ plus B. If it's less than 0, it should be equal to 0. So that's the definition of a ReLU, nonlinear activation function.
Oh, yeah. Okay,
right?
I got it.
So
Yeah, thanks.
yeah, so the lower and upper bounds, these two terms are used to help the encoding. So these are not our end goals. These are used to help you write the encoding, these two terms here. so that you can have yeah, so imagine that you don't have the lower and upper bounds. Then you cannot easily write the constraints. So yeah, suppose this lower is minus 100. Its higher is 100. Then this term says 100 vi greater or equal to z I plus 1. And the next says wz plus b greater than or equal to zi plus 1 plus 1 minus vi times minus 100. So if you didn't have this 100 minus 100 bound, then how do you write this constraint? Right? So so these constraints are necessary for formulating these inequalities.
Yeah.
Yeah. Okay. So then how do you get these lower and upper bound constraints? So there's a typo error. Here's the bound propagation. So if your input z is within a lower L and U, the bounds, then the output wz plus b is within these bounds, where w minus is defined as minimum of w and 0. W plus is a maximum of w and 0. So starting from the input x with its lower and upper bounds, notice that these are all vectors. Li is a specific element of the vector. And at every step, you propagate the bounds, and gradually the bounds will become looser and looser. So let's look at an example of how the propagation works. So suppose your W matrix is 1, 1, 1 minus 1, these 4 edges. Suppose there's no bias. And suppose your input x1, x2 has these bounds. Max is 0.3 for x1, 0.4 for x2, and min is 0 for x1 and 0.1 for x2. So that's your input constraint. And what's your output constraint? WZ, the matrix so look at this, look at the upper bound first. This equation. So W plus is this guy. You take you turn a -1 into a 0. W minus is this guy. You turn all the positive terms into 0. So this, if you do the math, it turns into this. And for the lower bound, the formula is this. So maybe let's look at a specific element. Say x3. X3 equals x1 plus x2 then its upper bound is the max of x1 plus max of x2. Its lower bound is min of x1 plus min of x2. Is that right? Yeah. So this is the right-hand side is 0.7. And 0 plus -1 is the left-hand side. It's 0.1. So it works out. And for x4, it's equal to x1 minus x2. Then its max is the max element, max value of x1 minus the min value of x2. Which is 0.2. Its min value is the min value of x1 minus the max value of x2, which is minus 0.4. So this expression, that is this expression here, just expresses the idea in a vector form. So to get a WZ's lower bound, whenever a scalar element of matrix W is negative, that is, this guy is negative, the corresponding entry in vector Z is chooses to be its upper bound, and vice versa. To get upper bound, whenever the scalar element of matrix W is negative, you take the corresponding entry in vector Z to be its lower bound, and vice versa. So whenever the weight is positive, then the upper bound of the output is the sum of the upper bounds of the input. When the weight is negative, the upper bound of the output is the negative of the lower bound. of the input. Okay, any questions? So, so given the so this is the final ARP formulation. Objective is this. That is the difference between the legits of the true label and the target label. You can add the softmax layer. It doesn't change the result because softmax is a monotonic function. So if you add a softmax operation on top of it, it makes no difference. So this is the simplified version, just to work with the legits directly. So so this is encoding of the ReLU with the previously shown encoding with the additional binary variables introduced. This is encoding of the input range, L infinity norm. This is the last linear layer. And in the encoding, there are these lower and upper bounds at every layer. And these are computed with these techniques. Starting from the input upper and lower bounds, you propagate it across across each layer. It gets looser and looser in general. And they're used in the formulation. And then you just feed the whole thing into Cplex or Gurobi. Gurobi is a backend solver, and Convex PY is a Python package for interfacing with Gurobi for solving a integer linear programming problem. And it'll give you a solution. And the solution is exact. So, so suppose your optimization objective is this, and we solve it for some y target, and the objective is positive. So suppose you have a binary classification problem with the true label of cat and the target label of dog. If your IRP solver tells you that this particular objective, after minimizing, the objective is greater than or equal to 0, then it is not possible to misclassify a cat image as a dog. So it's a certificate that there exists no adversarial example for that target class. Because no matter what you do, the cat label is going to get a higher legit value than the dog label. So you result, if you take the max of the legit, it'll always be a cat. And if you can prove this for all y targets, then this is a verified proof that there exists no adversarial example for this image. So for example, if you have a input of handwritten digit 7, if you perform the run the solver Cplex through it and get this value, then it means that it is possible that the target label to get a higher legit than the true label. So there may exist adversarial example for target class 0 or some other class. But if your result shows you that this is equal, the minimum value is 3.04, then there exists no adversarial example to make the classifier predict class 1 for this objective, because you're comparing the legit of class 7 with class 1. And if you can prove this for classes 1, 2, 3, 4, 5, 6, 8, 9, 0, and then you have proven that this classifier will never misclassify this input image for given bounded perturbation. That is, for the given bounded perturbation of epsilon ball. So notice that this proof is for specific input image, this particular image, and for a specific bound epsilon. So it's a very restrictive proof. It's
I
not
have a question.
yeah, sure.
Is this robustness also feasible for, let's say, ImageNet data sets that you have quite a lot of, like, different input data?
Well, it's always possible if you have a small enough epsilon. So, right? If you have very restrictive perturbations, then, I mean, theoretically, it's very intuitive, right? So suppose this is your loss surface, and this is your delta constraint, the epsilon bound, and perhaps this is the loss surface for the cat classifier, and perhaps loss surface for dog is in here. So whenever you cross this point, you misclassify it into a dog, because the loss of dog is lower. So the loss is inversely proportional to the legit, right? So if you make the delta, the range, large enough, you can always attack it successfully. You can always misclassify it. If you make it small enough, then it's always possible to make formal guarantees. It all depends on your bound. So so notice that if you're familiar with formal verification in software or hardware, where if you verify a piece of software, say a quicksort routine, to verify it correct, it means that this quicksort routine algorithm will always sort your input correctly, regardless of the input. So that's a very strong proof of correctness. But here, it's a little bit different. We are verifying the neural network in combination with the input image. So after you've performed the verification, you can only say that this particular input image with a particular bound, epsilon, can never be misclassified. You cannot say in general for any input image. So it's a little bit disappointing in some sense, because you're not verifying the neural network and certifying it for any input. You can only certify it for a given specific input. So any questions? So let's look at a final approach of formal verification via convex relaxation. So for a ReLU-based neural network, solving the integer linear programming problem with the added binary variables, encoding whether the ReLU is off or on. Remember that if VI is 0, so if you look back in the encoding, VI is 1 means that the ReLU is on, so you're in the positive part. If VI is 0, it's off. You're in the negative part. So this is the integer part in the integer linear programming. So if you didn't have integers, if you have a linear programming problem, the solving is not NP hard. It's very efficient. It's the integers that cause trouble. So with the VIs in the formulation, this is NP hard. And then to make it more computationally efficient, you'd perform convex relaxation and replace the ReLU constraints with their convex Hall, this shape. So it means that the ReLU can be partially off and partially on. So instead of these two line segments, you have this triangle. So you allow your output to fall anywhere within the triangle. So now the optimization problem becomes a linear program. There's no integers anymore, and it's efficiently solvable. So here's an example of the accurate ReLU encoding with the integer variables VI. You may have this as the final layer polytope, whereas with the relaxed convex relaxation, you may have a larger constraint, a larger bounds. And it's an approximation. It's a conservative approximation of the actual polytope. So it provides a strict lower bound on the IRP objective because the feasible set is larger. So in this figure, the blue star is the actual. So this loss function surface, given the delta bound, the blue is the actual maximum value. But the convex relaxation gives you the green star. So it's not actually achievable. The objective function never has this value, but it's a upper bound. So if the objective is still positive for all target classes, the relaxation gives a verifiable proof that no adversarial example exists. there's a little bit of confusion here because the lower and upper bounds. So here is the loss function, whereas for our formulation, we're minimizing the differences in legit. So in our formulation, it's so in the very original formulation, as we discussed before, we're trying to maximize the loss. Whereas for the IRP and LP formulation, we are trying to minimize this objective. So that's why we have this line here. So the it's actually a lower bound on the IRP objective, whereas it's the upper bound on the loss function. It's just a simple difference of minus sign. So given this lower bound, if the objective is still positive for all target classes, the relaxation gives a verifiable proof that no adversarial example exists. Because if the LP objective is positive, obviously the IRP objective will also be positive. If the LP objective may be negative for some target class, you can say nothing about existence of adversarial examples because it's a conservative, it's a approximation. So, and also solving the relaxed problem does not actually produce a true adversarial example anymore. That is, the relaxation may be able to construct an example with a negative objective, even though no actual example can achieve this. So, because your final bounds are relaxed, so that is, you may have points in your final bound in the green region that's not in the real bound, so they're not actually feasible. So that's why when based on the relaxed bound, it may be negative. You cannot really say if there's really any real adversarial examples. It may be just an artifact of your approximation. So for the binary exact formulation of the integer linear programming problem, suppose you have the optimization result of minus 2.54, then you can say that there exists an adversarial example for class 0 or another class. But with the convex relaxed constraints, if you have this result from your solver of minimum is like -6, then there may or may not exist adversarial examples. Because this particular minus 6.28 may be some point in the green region, not in the actual achievable region of your final layer legit. But if your result shows that the minimum value is positive, then you can say for sure that there is no adversarial example to make the classifier predict class 1. So you can imagine perhaps there's a bad region. If you go into this bad region, you misclassify the input. Then, if your relaxed bounds intersect with the bad region, it may be an artifact of your approximation. You may not actually, the real bounds may not actually intersect with the bad region. But if you can prove that your output, the relaxed bounds does not intersect with the bad region, you can say for sure that the real region will not intersect with the bad region. So a positive lower bound on the objective is a proof of robustness, but a negative lower bound is not a proof of existence of adversarial examples. So the benefit of having the convex relaxation is reduced computational cost, making the optimization problem tractable for large systems. The drawback is that depending on your approximation quality, you may not be able to prove robustness even though the actual real exact formulation can prove it. So here is a even coarser abstraction. So we propagate the interval bounds to the second to last layer, and then solve the minimization problem at the last linear layer. So minimize the last linear layer subject to this constraint. This is the result of propagating from the input layer by layer up to the last linear layer. So because the minimization problem is to find the lower bound and it's linear, so you simply choose ZD jth element is equal to lower bound if the CW, the jth element, is positive, and equal to upper bound if it's negative. So analytical expression of the solution is this. So these bounds are even looser, even more pessimistic than the bounds obtained by convex relaxation. There is no single input, even with relaxed activations, that creates these bounds on the legit differences. So every individual activation assumes that the previous layer could take on a separate set of values to minimize or maximize just that activation. So compare this to the formulation. Previous formulation, we still have this relaxed encoding of the ReLU. For the this interval-based bounds, we just get rid of the ReLU altogether, and only have the lower and upper bounds propagated layer by layer up to the last linear layer. So without the ReLUs at all, this is a very loose bound. So this interval-based bounds, I think in the tutorial, they used it for so this is the interval propagation-based bounds. So the advantage is that they are extremely efficient. There's no need for even the linear programming solver anymore. So this is the analytical solution. So these bounds are extremely fast to compute. And you can back propagate through them to actually train the network based on the robust criterion. So which is our next topic, which is to train adversarially robust models by solving the ultra minimization problem. So up to now, we have been acting in the role of the attacker and solving the inner maximization problem. So next, we will discuss how to defend against the attacks by minimizing the loss while having the attacker in the inner loop. So I think we'll stop here today. So the tutorial has this chapter on formal verification. If you try to run it, Carla and I tried it. It requires invoking a solver, Groovy solver, which is not available in the cloud. You can have it. You can download Groovy to your local machine and run it locally. But if you run it on a Colab, it's not going to work. Yeah. Okay. Questions?
I have one question here.
Sure.
If I get that the next lesson we're going to talk about how to develop or how to build a model that prevents adversarial attacks. But I'm thinking, can you also do that on a pre-trained model or when you do transfer learning? Is there a way you can also optimize the model in a way to prevent adversarial attacks, or you have to build a model from scratch?
Oh, so I mean, you need to you can definitely start from a pre-trained model and train it to be more robust. So the only difference is that from the standard training is the inner maximization problem. If you take out the inner max, then it's just the normal neural network training. So anything you can do with standard training, you just add attacker in the inner loop and find the disturbances delta. And so it's a form of data augmentation, right? So by adding more and more of these adversarial examples to the training set, your model will be more and more robust to these adversarial examples. So it doesn't matter if you start from a randomly initialized network or you start from a pre-trained network.
Okay, thank you.
Yeah. Okay, any more questions? Okay, so we'll stop here. See you next week. Bye-bye.
Thank you. Bye.